So today we're talking groundwater contamination remediation. We've now talked about wastewater treatment, drinking water treatment. Now we're talking about groundwater treatment. If groundwaters become contaminated, what are the various strategies we have to try to address that problem? What kinds of contaminants are present? That sort of thing. So there's essentially, I break down groundwater contaminants into three categories. The first is dissolved constituents. So these could be salts or nutrients, metals, things that we're familiar with that we think of as being potential contaminants in any kind of water. The second major category is called non-aqueous phase liquids, or NAPLs. And these are really common groundwater contaminants. They're liquids that are not that miscible with water. So a common class would be something like solvents that are used in various kinds of industry that could be spilled and sink into the subsurface and maybe not mix with the water so well. And then the third category would be maybe vapors that could come from those liquids, for example, and rise up through the subsurface and possibly sicken people who are living above where the contamination is. Where do these come from? Well, there's lots of potential sources of groundwater contamination, including septic tanks that aren't totally treating the sewage. So this could be a source for nutrients, bacteria, viruses. Landfills could have a wide range of organic or inorganic constituents leaking from them. Spills and lusts. Lusts as a common acronym in groundwater contamination. It stands for leaky underground storage tanks. These are found in just about every gas station has a underground storage tank that holds the gasoline, and many of these wind up leaking at some point in their lifespan, and so they can be leaking out gasoline, which would be a source of an LNAPL. So LNAPLs and DNAPLs stand for light non-aqueous phase liquids and dense non-aqueous phase liquids. One has a specific gravity less than water, the light ones. Dense ones have a specific gravity more than water, and so these don't mix with the groundwater. Some float on top, some sink, and we'll talk about those more in a minute. Mining could be a source of heavy metals, acids, or radioactive material, like as I mentioned, oil and gas. BTEX compounds, so benzene, toluene, ethylbenzene, xylene, or MTBE, which was a common additive in gasoline in California in the, I believe, 80s and 90s. It was added to gasoline to help it burn cleaner, which it did, but it was also, when you had a leaky underground storage tank under a gas station, the MTBE got into the groundwater, and it wasn't that toxic, but the main problem was that people could taste MTBE at very, very, very low concentrations. And so even at wells that were very far from the spill site, people were still complaining about taste issues. And so that's been phased out of gasolines. Treated wastewater effluent. So some wastewater effluent, whether it's discharged to waterway or it's spread on land to dispose of it, could also be a source of groundwater contamination. Agriculture, so pesticides and fertilizers, and then finally de-icing salts. De-icing salts, also de-icing chemicals that are used on airplanes. Both of these can sink into the subsurface and cause problems. So lots of sources. The point here is that most of our activities in everyday life have some way of contaminating groundwater. We don't see groundwater very often, and so we don't think about it very often. But there's lots and lots of potential sources of contamination, which is why groundwater contamination remediation is such a big topic and so important. All right, so non-aqueous phase liquids. As I mentioned, dense non-aqueous phase liquids. An example of this might be chlorinated solvents. Chlorinated solvents, one of the most common examples of these is a solvent called perchloroethylene. which is used in the dry cleaning process. And so there's all these little dry cleaners located around the country, usually small mom and pop shops, but they're using a very potentially dangerous chemical in many of them. And so a lot of them don't have proper procedures and safety procedures to keep those from spilling. And so just like gas stations are spread out everywhere, all of them have an underground storage tank. Dry cleaners spread out everywhere, lots of them. Many of them use perchloroethylene. And when perchloroethylene sinks into the subsurface, it can undergo transformations into trichloroethylene, dichloroethylene, and then vinyl chloride, which is the last step. And these have various carcinogenic potentials and have various means of treating them and cleaning them up, but it's a common dense non-aqueous phase liquid. And then L-naples, light non-aqueous phase liquids, an example here would be gasoline or gasoline additives, the chemicals that are in those as well. Both of these can result in long-lasting contamination problems that are not easily remediated. And so here's an example of an L-napple BTEX lust. Love all the acronyms here. Light non-aqueous phase liquid, benzene, toluene, ethylene, xylene, leaky underground storage tank. So here's our gas station with its leaking tank, and you have the non-aqueous phase liquid sinking down here, hitting the aquifer, and it doesn't mix very well, but it's lighter than the water, so it's going to sit right on top. And as the water flows by, some of this is going to be dissolved into the groundwater aquifer. Not all of it, but it's going to slowly leach into that water and be carried downstream. So this is one kind of problem, but an even harder kind of problem to deal with is the D-naples, the dense non-aqueous phase liquids. Here's our dry cleaners up here with the storage areas of the drums back here that are leaking. So in this case, it's going to sink down, hit the aquifer, and keep sinking down. It might get trapped in these like low permeability areas in the subsurface. And you can see some of it is getting, as the groundwater flow comes this way, some of that again is going to dissolve into that groundwater flow. And but then other portion of it might sink down into a low-lying area of bedrock or low permeability area. And these kind of dense spots that are in these low permeability areas can just stay there for a very, very, very long time, constantly contaminating the groundwater. And how do you go about addressing those is the challenge. So we remember Darcy's law from both geotechnical engineering and water resources engineering that says the velocity is equal to the negative hydraulic conductivity times the head gradient. Now, this isn't a particle velocity, but this is sort of a bulk flow velocity in the subsurface. And that's what the water's moving, but the chemicals that are in the water may have some sorption or some desire to bind to particles that they're moving past. And so that sorption slows the chemicals down. And so we have a way of characterizing that, which is called the retardation coefficient. Retardation coefficient is 1 plus the bulk density divided by the porosity times K sub D, K sub D being the distribution coefficient that we learned about back in the sorption chapter. It's the ratio of the concentration sorbed to the concentration in the water. And so the higher that is, the higher the retardation coefficient, which means the water's moving along, but the chemical likes to sorb, and it might be a long time before it redissolves back into the soil, or it sorbs and redissolves, sorbs and redissolves, or it might sorb irreversibly and just stay there until maybe all those sites all the binding sites are saturated, and now things will bind further down, and either way it looks like a slowing down of the chemical. And so the actual velocity of the constituent, the dissolved thing or the contaminant, is the Darcy velocity divided by the retardation factor. So the higher the retardation factor, the more strongly it sorbs, the slower it's going to move. Okay, so what are the remediation techniques? There are lots and lots of these. I've broken them down into biological, chemical, and physical techniques, and I'm going to go through each of these briefly. There's tons of good information about this on the web, as well as in your book. The section on this is quite good. It's short, but a good read. So let's start with biological methods with natural attenuation. Natural attenuation is a process where we're going to let natural occurring processes basically address the problem. So we have, so whether that be to lessen the mass of the plume, lessen the toxicity, how mobile it is, whatever. And so what are these processes? Well, there's biodegradation. So there's microbes in the subsurface that are degrading the compounds. Dispersion, or both dispersion and dilution, serving to spread out and dilute, lower the concentration of the toxicant. Absorption, volatilization, transfer into the gaseous phase and then up into the atmosphere, or other like abiotic reactions, physical chemical reactions in the subsurface. So all of these things are happening. So if we have a spill, we might say, let's let nature take care of this spill. But in doing that, we're not saying we're going to do absolutely nothing and just leave it alone. If we know that the plume is there, we know it's a threat, and we want to use natural attenuation as a technique to deal with the problem, we still need to know a lot about the plume's behavior, how much there is, how big it is, what its rate of travel is, and we have to be doing a lot of monitoring in order to establish that it's working, right? So if we're concerned about a well downstream or wildlife in some spot that the groundwater re-emerges, we don't want to just say we're not going to do anything because it could be a threat to those receptors, the well or the stream. If we're going to say let nature take its course, we need to document and establish that that's going to work before problems start occurring. So here's an example of natural attenuation. Is we have a BTEX species, so from gasoline. These can often be degraded by native microbial communities using available electron acceptors. So we didn't talk a lot about redox reactions in this class. But redox reactions are reactions that are often mediated by biological organisms, but it's a chemical process and it requires some sort of electron acceptor and then some sort of electron donor. Now, often the electron donor is the compound itself, like the BTEX compound itself. It could also be some other electron donor. But then the electron acceptor is more like, what is the organism breathing? We breathe oxygen as part of our respiration. A lot of microbes also do that. But there's other electron acceptors that they can use as part of that redox process. So if you've got this little microbe here and you've got oxygen or nitrate or sulfate present, you've got the carbon source, that's the electron donor, maybe the BTEX compound. You've got the right environmental conditions. You've got some nutrients. This guy can happily go about his business converting the BTEX compounds into water and carbon dioxide and just dealing with the problem. But if you don't have the right conditions present, then that might not occur. And we didn't talk a lot about redox reactions, but there's multiple different electron acceptors. There's different rates of reaction using those different acceptors. And so it tends to be that if oxygen is present in the subsurface, you will have aerobic conditions. Oxygen's the fastest. It has a lot of energy associated with that respiration, that redox reaction, and you'll have aerobic organisms using oxygen to degrade the stuff. When oxygen is depleted, or if it's not present, then we'll move down this sort of electron acceptor tower to the next available electron acceptor. So if oxygen's not present, maybe nitrate's present, and we can get nitrate-reducing organisms to do the reactions. If there's not a lot of nitrate, there might be a lot of sulfate, and so we get sulfate reducers. There's also manganese reducers, iron reducers, and then methanogens are the lowest, where even when there's none of these other things, if we can have methanogens can be present kind of in a lot of different cases. So we like oxygen aerobic organisms because they are fast at degrading things, but they're not always present. Now we might want to use natural attenuation, but the conditions are just not quite there to allow that to work. So if it's not fast enough, it's not complete enough, or it's not happening frequently enough, we could do different things to make the process better, and that's called enhanced bioremediation. And this could involve several techniques. One could be bioaugmentation, where we inoculate the subsurface with specific strains of bacteria that are good at degrading the contaminant we have. It could be bioventing or biosparging, where we're adding oxygen or nutrients to help the process along. Or we could add electron donors. So sometimes the concentration of the species is low enough, or it doesn't have enough carbon material in it. We could actually add things that have carbon in them that are electron donors. So sugar has a lot of energy in it. We could add things. I've seen cases where they've added molasses or where they've added methanol, which are carbon containing, to give more electron donor to the organisms down there, essentially feeding them. So those are a couple biological processes. And then we've also got chemical processes as well. So permeable reactive barriers. This is actually kind of both physical and chemical, where we could have a source in the subsurface that's getting pulled along by the groundwater. We could actually put a big barrier in place that we still allow water to permeate through, but that as it's doing it, there's something going on that's treating what's in there. So zero valent iron is a very common one. Basically, think of this as like iron filings, that the surface of that iron mediates a chemical reaction to help oxidize and break down the chlorinated solvents. A granular activated carbon, so basically a big carbon filter that sorbs the contaminants out. Or bubble walls, where we could put in a barrier and actually add oxygen to bubble up through, and that could either strip the compounds into the bubbles that then go to the surface and volatilize, or it can just be adding oxygen to help there be aerobic conditions down gradient of that. This is just another picture of what's going on there, where you have a plume, maybe a LNAP or a DNAPL coming through, and a permeable reactive barrier, clean water on the other side. Trees are happy, trees are sad over here, that sort of thing. My favorite is phytoremediation. This means basically trees doing the remediation. They can be planted to treat various constituents, including most common being metals, but also could be useful in some of these LNAPLs and DNAPLs. Also can treat methane from like old landfills that are releasing methane. You could plant trees in the landfill caps. In fact, for graduate school, I almost wound up going to University of Iowa to work on phytoremediation stuff for my research. I wound up going to UC Davis, where in California, I was told phytoremediation isn't used as often because we need to water the trees, and water is too valuable in California for this kind of a technique to be useful. Not totally true, but I didn't wind up working on this that much in graduate school, but it was always kind of a fascination of mine. And you can see on this diagram lots of different actual processes through phytoremediation that it works. Either the roots actually extracting like the metal from the groundwater, or just attracting the contaminant to the root zone and keeping it there. Degradation that can occur either in the roots or the leaves. Volatilization that can happen by taking up the water through the tree and then transpiring it into the air. anyway, you could then wind up, maybe the tree winds up with a high burden of metals in it, and eventually you harvest the tree and grind it up and landfill that in a hazardous waste facility or something like that. So typically you see like these hybrid poplars planted with these situations where these super fast growing trees, really good at extracting lots of water. You might see like lots and lots and lots of rows of these super tall, fast growing poplar trees. I've seen some of these facilities in Oregon. I think if you drive 84, I think it's 84, out towards like Pendleton area or the Dalles, if you keep going, eventually you see a site on the right that I believe is a contaminated site from historical either solvent manufacturing, or maybe it's an old munitions plant or something like that. So you can see this big giant field of planted hybrid poplars if you ever go out that way, and that's what's going on. Okay, next one is in situ chemical oxidation. This is, or ISCO. The idea here is we're going to add strong oxidants to oxidize the contaminants to water or CO2 or other substances. We already mentioned oxygen, but also ozone, hydrogen peroxide, or permanganate. The idea here is we drill a well, we have a tank of these chemicals up here, and we're actually pumping them down into the subsurface and treating the area that the contamination is in as we're doing it. Groundwater remediation goes through various sort of stages where different processes are popular. In the 2000s and maybe the 90s, natural attenuation was really a popular method where we were starting to understand the dynamics of what was going on in the subsurface good enough that maybe the most effective or cheapest way of addressing it was natural attenuation. I would say in situ chemical oxidation is one of the more popular methods nowadays because the chemical cost has gone down, our understanding of what can happen in the subsurface has improved, and we've maybe gotten a little bit more aggressive at treating some of these issues earlier on when we detect them instead of letting them go for so long. So this is a common method used now that was not used as much 20 years ago. But this is the idea here. A couple other physical methods, so source control. This is like we've got our tanks, our solvent or oil that are leaking. Hey, let's dig them out and get rid of them. Good idea. The problem is that, of course, the contamination has already left the building. So it can remove the original source of contamination, but maybe not the current source. Maybe the current source is now this DNAPL right here. So it's still important to address the original source, but it's not all we need to do. Another physical solution is just source isolation. If the plume is limited in extent, maybe we can actually dig down and maybe build walls or barriers to keep the contamination in one particular area. And also that can work in certain circumstances. So like this is where an example where it might work of we've got the contamination here, maybe a DNAPL that's constantly leaching into the aquifer. We build these barriers and we cut off that source, and this stuff winds up eventually going away, and now this is protected and eventually will go away. When it might not work is if we don't have this confining layer on the bottom, we can only go so deep with our barriers, and the DNAPL may just sink right below where we put our barriers and keep moving on. And then pump and treat. Pump and treat was one of the very first methodologies that was common back in the 60s, 70s, 80s for treating contaminated groundwater. Simple concept of let's pump the contaminated groundwater out and let's treat it at the surface using the wastewater and water treatment techniques we've already talked about, and then maybe re-inject it into the groundwater or discharge it into a surface water. Really simple concept. Problem is that you get really slow mass removal of your compounds, especially if they're strongly sorbing, or they've migrated into very low hydraulic conductivity, low permeability layers. So you've got this treatment facility that you're operating at the surface. It may take 20, 30, 40 years to completely treat all of the stuff in the subsurface. That's a long time to be operating a full-on treatment facility. So not nearly as popular as it once was, but it can be appropriate depending on what the subsurface looks like and what the chemical is. And then the last one is multi-phase extraction. Multi-phase extraction uses vacuum pumps. So it's a combination of a pump that could take out water as well as vapors and air. And the idea is that we're pumping that out, and again, we're treating it somehow. So sort of like pump and treat, but also addressing the vapors if that is one of the contaminants that we're concerned about. So as we do, we suck all this stuff into the well and pump it out. We can treat the vapors and the liquids through that. So again, similar to pump and treat. And in reality, many times the contamination is addressed by some combination of these different methods. So I know of a fairly local site that's within 20 miles of here where they're using multi-phase extraction to keep vapors at the surface from being at toxic levels. They're using ISCO, the in situ chemical oxidation, to address sort of the hot spots of contamination that they know about in the subsurface. And they're using natural attenuation to address where the plumes become more disparate and widespread but at lower concentrations. They're using all of those methods to address the various problems that these spills in the subsurface manifest themselves in. So again, this is really common. Environmental engineers tend to, if they work on these kinds of projects, they tend to become specialists in it, and they work on lots of these. There's lots of contracts with the federal government for military installations, with chemical companies, the DuPonts and Dows of the world that might have spills or contaminated sites, as well as just with oil and gas companies to address leaky underground storage tanks and things like that.